All right. So our next speaker is José Abellán, who will be giving an invited talk. Jose is an associate professor with the Polytechnic School at Universidad Católica de Murcia in Spain since 2014. So he'll be giving a talk on multi-GPU coherence.
Thank you very much, Daniel. I'm going to share my screen.
All right.
Okay. Can you see my screen?
Yep.
Okay, nice. So I'm going to put here. Okay. Okay. Okay, thank you very much for the introduction. So this work has been possible thanks to the collaboration among different institutions, Boston University, Northeastern University, KAIST, and UCAM. And this is the outline of my presentation. So first, I'm going to give some introduction to multi-GPU system very briefly, to DNN training, because also DNN training will be used as an example of why do we need MGPU system, a multi-GPU system with true shared memory. What is our proposal here? And I'm going to explain later on the MGPU-TSM and also with the Coherence protocol that we also have envisioned. Finally, I'm going to give you some conclusions. So deep learning is everywhere. Everybody knows the different applications that it supports and enable. DNN training, the thing is that it can take days, weeks, or even months in order to have a training model that could be deployed with high accuracy. And for that, in order to accelerate the process of training, it has been proposed the use of accelerators, such as GPUs, FPGAs, or TPUs. And in this talk, I'm going to focus on the multi-GPU systems. Some multi-GPU system, we have different solutions, depending on the different vendors. We do have DGX2, 1, and 2 from NVIDIA, and also Instinct M100 from AMD. And in order to program these supercomputers, we have different solutions as well, such as TensorFlow, PyTorch, or MXNet, among others. So just to recall the different stages of the DNN training process, we have the forward propagation, we have the backward propagation, in which we estimate the gradients, and then based on these gradients, we update the weights, and then we have a new DNN model with another weights, new weights, that will be used to process per iteration, and then estimate the evaluation metric that basically estimate the accuracy per iteration until we reach some convergence. So if we want to distribute the computation of the stochastic gradient descent algorithm in order for the training process in a multi-GPU system, so and assuming a data level model, data parallel model, we see that the CPU here, and this is a multi-GPU system with 4 GPUs, the CPU just broadcasts the DNN model to the GPUs, then each GPU runs its own forward propagation, backward propagation, according to a subset of inputs, for example, images from ImageNet. And based on that, after the backward propagation is performed, then we can have the gradients, but the gradients need to be reduced on a single GPU, in this case, GPU 0. And by using this reduction tree, right, we have in GPU 0 the average values of the gradients that will be used by the GPU 0 to update the weights. And then the new DNN model weights are broadcast to the remaining GPUs in order to continue the process of training. So as we can see here in this stage, which is the weight update stage, there is communication across different GPUs in the system. So in order to support communication in a multi-GPU system, we have different solutions that the programming vendors use. We could have and extend the main copy approach that in the previous presentation has been described from host to device, device to host, depending on the stages in the computation. We could extend this model for a peer-to-peer main copy or peer-to-peer data transfer, where we have the 2 GPUs by using the system of data transfers from copying data from one GPU's memory to the other one, so that the other one, which is the requester of data, can start processing from the local memory the computation. So there is another extension in which the GPU that wants to access to certain amount of data that is inside another GPU's memory uses a peer-to-peer direct access, basically caches the data in the cache hierarchy of the GPU1, So there is no use of copies here. There is no, it avoids to waste, store data here that could be, could occupy GPU's memory for other uses. So this is another solution in order to share data across different GPUs. So and then we have one extreme in which we devote the runtime, in this case for CUDA, for example, in a solution that is called unified memory, where all the memories act like a single piece of huge memory, and using virtual addresses, then all the devices, CPU or GPU access to data, and the runtime is responsible for moving data at the granularity of pages, so that there are page faults, page migrations, and the advantage in terms of programming is trade-off for a degradation in terms of performance due to these page faults and page migrations. So these kind of communications happen in a multi-GPU system, and we have used them in order to program a DNN training workload. For that, I'm going to focus on our work that we have published in ISWC in 2018, and especially for the results for experiments carried out for the DGX1 Volta. There are others pre-Volta, but we are going to, due to the brief open talk, I'm going to focus on the Volta ones. So the Volta-based DGX system is like this at the very high level. So we can see here multiple GPUs, Volta GPUs, 8 in particular, that are connected to each other by using different technologies, a symmetric network that is based on a hybrid cube, where we have NV links, and we have also PCIe Express links, and the CPUs connect each other by using interquick path. So this creates a NUMA effect in terms of memory allocation. So that is quite important to fully understand where the data is, where the compute is, in order to exploit locality of data, so that we can take full advantage of this supercomputer. So in order to understand how, by using this multi-GPU system, how deep learning can impact in terms of performance due to the communication stages and the different stages of DNN training and all the communication that happens during this training, we have used different DNN models that have different characteristics in terms of weights, number of layers, types of layers, etc. And for the ImageNet dataset, we have used different experiments for short scaling, weak scaling, etc. And for certain batch sizes. So essentially, we have compared two solutions, two implementations for DNN training. One that is based on peer-to-peer data transfer, peer-to-peer copy that I explained earlier, and another one that leverages the use of nickel that mostly relies on peer-to-peer direct access and simplifies a lot programming because we can leverage its or reduce, broadcast, this kind of collective operations that are implemented here efficiently. So in this work, basically, we wanted to answer some questions such as, okay, what is the scalability of DNN training as GPU count increases? What is the comparison in terms of two different communication mechanisms that is based on peer-to-peer data transfer, the other one that is relies on nickel? What is the impact on network size for the DNN models, the batch size, etc., and also with respect to the GPU memory utilization? And here I summarize just a couple of slides of results. So in this case, we have here 8 charts. So the first row of charts correspond to our implementation using peer-to-peer data transfers. The other one is the second row for nickel. Then its column corresponds to a particular DNN model, Lanet or Inception. And then we have here 4 bars that correspond to 1 GPU, 2 GPUs, 4 GPUs, and 8 GPUs. And here we have 3 different batch sizes, 16, 32, and 64. So as we can see here, there is a trend in which as we increase the batch size, we get better, lower total training time. And also as we increase the number of GPUs, again, there is a good trend in scalability. So, but this scalability depends on the implementation. So if we take a closer look at the implementation peer-to-peer versus nickel, So of course, it scales, as I showed earlier, but not at the same pace. So in particular, peer-to-peer outperforms nickel because mainly because the use of peer-to-peer direct transfer versus peer-to-peer direct access in case of nickel, that introduces some kind of serialization when multiple GPUs access to the same cache, remote cache line and need to be cached locally. And also there is a minor initialization overhead that requires nickel that is more marginal as we increase the DNN model size. So essentially the message is very powerful, which means that, okay, if we change the communication mechanism, then performance could matter a lot and it could impact a lot, the speed ups numbers that we could get. So another thing is important is that, okay, with respect to the total training time, what is the percentage of the weight update stage of DNN training with respect to the, the other stages? So we can see here that it is not marginal, and this communication intensive phase, the weight update that basically is used for transferring gradients and weights, as I showed earlier, will demand a very good care in terms of how you program this stage to get good performance. So our observations, according to these experiments and other analysis that we have done in the paper, so that, okay, communication happens between GPUs. The types of communication matters a lot in terms of get better performance. The asymmetry of the DGX1 network topology matters a lot in order to get better speed ups numbers. And of course, there are other conclusions. And we see what is the trend in terms of DGX development across different generations. So we have here the Ampere, for example, where the piece of memory per GPU has increased significantly from 32 gigabytes to 80 gigabytes. Also, the GPU to GPU connectivity has improved a lot. We have 600 gigabytes in Ampere. But if we see the Hopper, the latest, the recently released DGX GPU architecture, essentially Hopper, so we see that per GPU we have the same amount of memory, but we use a more advanced memory technology that provides 2x more bandwidth with respect to the Ampere. But also looking at the links, we see here from 600 gigabytes to 900 gigabytes, right? And one important aspect as well is that goes into a coherent solution onto a shared memory system between the CPU and the GPU, because these MB links for the Grace Hopper superchip allows coherency between the CPU and the GPU by using a shared memory. So this is very powerful and a very good introduction for our work that we present here about MGPU-TSM. So now if we see the MGPU-TSM, and this is one example of a contemporary multi-GPU system, this is a system that is composed of 4 GPUs. So just to recall, the GPU includes a cache hierarchy, right through caches, L1 caches, right back L2, then we have local access to memory, and then we have an RDMA engine that is responsible for doing remote transfers between different local and remote main memories that could degrade bandwidth by 10x, depending on the technology. So another thing is that in order to do all these peer-to-peer copies, so there will be a lot of inefficient U-memory usage because, there will be replication of data. So if we provide some support, hardware support for cache coherence, as I'm going to present later, you will be able to avoid these multiple copies. So we will have basically a single copy of data and the other GPUs will be access to it. The problem is that this NUMA effect, this interconnect that is placed here. And our approach is just to move the interconnect, not at this level, that is the traditional multi-GPU system, but in the middle. So that instead of having just multiple speeds, that is the non-uniform memory access, depending on whether the GPU access to the local or to a remote memory through RDMA, we will have basically that all GPUs and even the CPU can access to the memory banks with a two-hop distance. So this basically gives us the illusion of a UMA-based system, what will simplify a lot the programmability of it. But of course, this will degrade performance if it is not implemented well. This switch, this interconnect, this is called a switch, but it can be whatever in order to make it much more advanced. Maybe this could be some kind of topologies that allow all the connectivity between them, indirect or direct topologies, crossbar or butterflies, depending on the topology and the what is the target destination of the multi-GPU system. Another important message is that the GPU's L2 caches will access to the entire memory space. So in a regular multi-GPU system, we have an L2 cache that access to memory bank and is private to it. But in this case, we need to give support to all these accesses. So this MGPU-TSM architecture has been proposed, and we are going to see what is the performance as compared to the regular multi-GPU system that uses RDMA. And later on, I'm going to compare it against another one that implements the unified memory solution. So in order to do the comparison, basically we use our NGPU sim simulator that we published in ISCA 2019 for a certain amount of applications from different application domain, from deep learning and also from cryptography for a 4-GPU system. So the experiment star results are the following. So these are the benchmarks. This is normalized execution time against the MGPU RDMA system, the baseline. And then we observe here the differences in terms of performance for the MGPU-TSM, which is the dark blue bar, and the other one which is used the RDMA-based system, but assuming a unified memory solution. So as we can see, MGPU-TSM is 4 times better than the baseline. And as compared to the unified memory solution is even almost 12. Okay, but this is the first part of the story. The second part is, why don't we add coherence, a coherent protocol, in order to simplify a lot the implementation of applications in MGPU-TSM? And that's why we question ourselves about, okay, why coherence is needed in a multi-GPU system? So as we can see from the multi-core, multiprocessors, same memory-based system in general, that it is sharing of data. And at the same time, it simplifies programming, even though you need to deal with barriers, atomic operation, etc., in order to make it work for certain applications. But at the end of the day, it improves a lot memory utilization because you avoid all the replications. Okay, so taking a closer look at multi-core coherence protocol, hardware coherence protocols, such as MSC, MESI, MOESI, etc., the problem of them is that as you increase the number of cores, the number of threads in the applications that need to be, shared data, the problem is that you enter into a prohibitive amount of invalidation traffic. So in a GPU that has thousands of cores, so this kind of protocol don't work. So in order to take advantage of a hardware coherent protocol, we took a look at the GTSC protocol that was published in HPC 18, that target a single GPU system and use the idea of timestamp-based coherence. We basically leverage it and build on top of it and create our new coherence protocol, targeting our MGPU-TSM. So how a timestamp-based coherence protocol works? So basically, as we can see here, this represents the accesses to a cache line in a cache, and then we would have a hit or a miss, as you know. But in this case, the hit or a miss depend on the list. The list is basically a logical time between the write timestamp and a read timestamp. These are operations that happen to this particular cache line. And then we have a cache. The cache contains another timestamp, which is called CTS, that is general for the cache. These are values that are depends and are independent for each of the cache lines. But this one is updated for each write operation on the cache. So if you read or write in the cache, if the CTS falls between these two margins, in this segment, you have a hit, otherwise you have a miss. So leveraging this idea, I'm going to expose here just how our new protocol, coherence protocol, that is called MGCC, works. So you have here two different GPUs, GPU 0, GPU 1. And I'm going to show here a timeline for inter-GPU coherence. Our protocol also works for intra-GPU coherence. So in this case, we have a compute unit, L1 cache, L2 cache, a memory bank, and the same for the other GPU. And then, as we can see here, as due to the cold start, for certain amount, 3 instructions that runs on this GPU, another that runs on this other GPU for 2 different locations, X and Y, that are in different cache lines. So the CTS is 0 due to the cold start, as he mentioned. So our cohesion protocol works as follows. Once you have the first operation, the read on X, you have a miss here, you have a miss here, and then what does it happen? So when it reaches the memory, so we assign a list. A list in this case is 10, but it can change depending on the operation. And effectively, it depends whether it is a read or it is a write. I'm going to show 2 different values for read and 1 value for write later on. So look at here. So for the X position that you are going to read, essentially you read the list as well along with the data. And here you have a couple of numbers. These couple of numbers that are stored for each cache line, in this case is 0 and 10. This is the WTS and this is the RTS that I showed earlier, WTS and RTS. So this is 0 because it has never been written, and this is 10 because we assign a list of 10 for each read operation. So as you can see here, it is synchronized from the lower level of the memory hierarchy to the higher level of the memory hierarchy. So that as we can see here, this is a cache miss, and the list have been updated these 2 values along with the CTS that is represented in brackets. So for the perspective of the other operation of the GPU1, that is a read on Y, so we can see that the CTS is still 0 for this particular cache. This is a miss due to the cold start. And in this case, the release is 7 instead of 10. Okay, this is another example. And the idea is the same, 0, 0, 7 instead of 0, 10, and 0, 7, and 0 with this the CTS. Now, what happens is that there is a write on Y. Since this GPU has never access to Y, then there will be another miss that goes, in this case, to the memory control, of course, to the main memory. So looking at the list of Y, we can see here the Y, the list was 7. And now what we did in our implementation is that we augment the list by 1 value that will represent the new CTS and the new RTS and the new WTS, sorry. So 7 plus 1 is 8. So this will be propagated to the WTS and also to the CTS for the next time. And then we add another list for the reads. In this case, the list is 4. This is for the writes. I said that there will be 3 different lists, 1 for reads for the GPU0, 1 for read for the CPU1, another for writes that will be also 4. So 7 plus 1 is 8, 8 plus 4 is 12. And this will be the list for Y. And this will be the list for the read TS, so the other timestamp value. And then this will be how the different, for this particular cache line, the lists will be stored. Okay, so what does it happen now? So take a look at here. Now I'm going to write on X, and the process is the same, exactly the same. We have a miss because X has never been read by this GPU. And then once the X, the petition, the write petition reaches the memory, then we need to see the list. In this case, for X, the list was 10. Okay, 10 plus 1 is 11, what will be the first value? 11 plus 4 is 15, which will be the final list of the X. That will be, update the values as it is done here, as similarly to what we have done earlier. And then the CTS will be 11. Okay, we have misses, a lot of misses. Now what does happen here? We have a hit. Here we are going to read X, and since X, according to the list, is between 0 and 10, and the CTS value is 0, it's 8, sorry, 8 is within the list. So we have a hit here. But the problem on the other hand is that the GPU1 needs to read Y, and Y, the problem is that the list of Y is, according to this, is 0 to 7, and the CTS is 11. So this falls outside the list, so you will have a miss here. So basically it's a self-invalidation, basically. So the petition goes here to memory, and in this case, we are going to see the list of Y. Y is 12, 12 plus 7, which is the value that we assign to reads as according to this part that remember this part, right? From 0 to 7, right? Now from 12, another 7, which is 12 plus 7 is 19. So we have here the other list, the final list for Y. and then it is propagated as it is a read as before. So essentially, you can see here that according to the timestamps, according to the CTS, RTS, WTS, you will have different memory orders, you will have hits and misses. And this is how, essentially, for a very simple example, how the MGCC protocol works. So how are we going to implement the MGPU-TSM system along with the MGCC? So as I mentioned, we put the switch here at this position, and we are going to re-architect the memory controllers. So we are going to unify the memory controller, because now we could have different petitions from different L2s to the different memory banks. And we implemented here a request tracker that essentially allows us to reorder memory petitions to the different memory banks so that we can implement different consistency models. Also, we have here the TSU. The TSU is basically to store the different timestamps of the coherence protocol. So we compared the performance as it, in order to simplify the implementation, we assume here that the L2 caches that are write back are changed to write through, because it simplified a lot the implementation of MGCC. So in terms of performance, what is the performance degradation or optimization if we change the L2 cache from write back to write through? So this can be measured here. So we have, for the different benchmarks, the first bar correspond to our MGPU-TSM with write back caches, non-coherence, that we don't implement here the coherence protocol, and for relapse consistency. And we compare directly peer-to-peer against changing the cache to write through. So we can see here that in terms of geomean, the performance degradation in marginal is 2%, more or less. But if we incorporate the coherence protocol, of course, we will expect that adding coherent solution will degrade performance. And the performance degradation is still tolerable, is assumable from 2% to 21%, depending on the memory consistency model we are implementing. If we are assuming sequential consistency, because it doesn't allow any memory reorderings, so we have a major hit on performance as compared to the other one that is based on relapse consistency. Okay, finally, I'm going to we compared our coherence protocol against the state-of-the-art for multi-GPU systems that is called HMG. HMG was published in HPC in 2020. It is based on a valid-invalid coherence protocol, but it relies heavily on scope-based consistency, what of course requires more programming effort. So we avoid the programming effort, and as we can see here, we compare our solution against MHE, and we observe that our solution performs 2.4 times better than the state of the art. Finally, I'm going to give you some conclusions. So first, we identify why do we need an MGPU-TSM system with coherence protocol, hardware coherence protocol, according to contemporary workloads from deep learning. Then we have identified hardware and level limitations, software limitations of contemporary multi-GPU systems, and we propose MGPU-TSM plus the coherence protocol. So as compared, without considering coherency, the maintenance of coherence, we can see that our solution is much better than the baseline. Also, we add the coherence protocol, there is a performance degradation. But this performance degradation from 2% to 21%, depending on consistency model, is also a good advantage for us because we avoid a lot of programming effort, but at the same time, we are getting very good numbers as compared to the state of the art with this HMG, as much as 2.4x better performance. So finally, I'm going to acknowledge all my team, especially Saiful, because this was basically his PhD work that I'm representing here, and many other very wisdom people from other institutions. And we have been able to publish many different papers regarding multi-GPU systems, MGPU in simulator, etc., that is helping to us to continue our progress in the research front. So thank you very much for your attention, and yes, please, questions.
All right, thank you. So if you have any questions, feel free to unmute yourself or type in the chat box. So I'll just start it off with one of my questions. So in one of the slides, one of the main changes that you did to the MGPU-TSM is that you switched the switch, right?
Yes.
Between the memory and the GPU.
Yes.
This reminds me a little bit of how disaggregated servers are, where basically you can have racks of CPUs or GPUs and racks of memory, and they're kind of connected to a backplane. So can you comment how potentially your techniques can scale to a disaggregated server type of environment?
Yeah, that's a very, very good question. So here we are considering just a single node multi-GPU system, but for sure it requires more, a more advanced interconnect topologies in order to make it scalable, and also the use of different technologies. For example, we are observing and we have analyzed that going beyond a single node, we would need the use of, for example, silicon photonics, in order to make more, provide enough bandwidth, and also provide enough, the latency that is required in order to give us the illusion of this unified memory architecture. Of course, this could be, implemented. We don't reach this UMA effect. There will be some performance degradation, but of course, this will be, something to explore and to consider in order to map the application more, in a more intelligent way, in order to make the system more scalable. So that's something that we also have, exploring as part of the extension of our work. Yes.
Great, thanks. All right, any other questions? Okay, so if there's no questions, all right, let's thank our speaker. Virtual clap. Okay, and then we'll move on to our next speaker.